Dr. Rajat, are you there? Your voice is not audible and screen is also not visible. If there is a connection issue, Dr. Rajat.
Am I audible?
Yes, you are audible.
Okay,
Slides were a little hazy. That was,
just a minute, Professor. Now it's visible.
no, it is not visible yet.
Please confirm.
Yeah, it is visible, but I think it is a little bit of hazy. Slides. Yeah.
Okay, shall I start?
Yeah. You can continue. It is good. Good.
So actually, this time, so what we are looking for and what kind of the problems we need to be addressed. So the conventional alloys, these are the alloys is are not qualifying. Approximately 30%. Actually, based on the literatures, 30% material losses in the corrosive and the harsh environments effects, because due to the temperature, certain temperature changes in the aerospace or aircraft or spacecraft, their materials, because they are having certain temperature changes, and due to the sudden temperature changes or layer or atmospheric moistures or dryness, it's going to corrosions and harsh environments effect. So 30% of alloys is going to disqualify based on this particular, and they are having the weakening above the 600-degree temperature. Beyond the 600-degree temperatures, if they are going to use, so it's having their lot of difficulties. So nowadays we have to be think on that particulars where we can develop which can be sustained above 600 degrees Celsius metals, like, and it is having the high entropy alloy, because it's the combinations different alloys or elements. So in that we are having the capability to develop, and it may be survived or sustained there around at the 1500 or 2000 degrees Celsius, and 50% is structural failures occurs due to the conventional materials, because they are having the very different properties, and that particular properties is not going to sustains during the harsh conditions, and we can say that the higher temperature sites, once it is the higher temperature site, the materials is going to fail. So basic principles we are very clear and we know, but it is a very basic principle. So once we are talking about the mixing of the particulars properties, there are the pure substance and mixing. So elements and compounds, they are the different part. This is pure substance. So mixers is the homogeneous and heterogeneous. So we have to be focused this on homogeneities, and there are the following properties we have to be taken care: the atomic size of the elements, what kind of the atomic size we are taking care, excuse me, and there are the bonding natures and chemical compatibilities, as well as the density. Density is the very important parameters during the mixing properties, because the based on the density we are going to decide these materials properties and their ranges, whether it is the low entropy alloys or medium entropy alloys and high entropy alloys. So let's see the type of the materials which is being used in the spacecraft or the space structures. So these are the most exhibit the high strength to weight ratio, and it has the thermal stabilities as well as the resistance to the harsh environment. So these are the this space the materials has been the that the systematic diagrams has been taken from this the particulars the Vega's spacecraft structures, and we can see how this particular the small components they are going to fabricate, and that components it has to be sustains the high temperatures environments. Without the sustaining the high temperatures environments, it cannot be possible to survive. For that, basically what kind of the materials that traditionally we are using, either it is the titanium alloys or it may be the carbon fibers composite. So these kind of the combinations of these metals or non-metallic materials we are going to design and using in the structural materials. Let's will we see the thermal protection systems is too much required once we are talking about the high temperatures, as well as once we are go for this other sides, there are the different temperature variations. Once it is the ground level, there are the different atmospheric temperatures, gravity, and their temperatures. Once it is in the air, so there are the little bits different or slightly, we can't say it is the very big changes of their atmospheric pressures, gravity, as well as the temperatures. So we have to be taken care of up to this the thermal property systems. Now another point is once it is the high temperatures we are talking, that times we have to be see in the radiation resistance materials. If the radiation is the not is the very reasonable or very the limit which can be we are sustained, so it's very difficult. So we have to be taken care about the radiations part also. Here over this you can see there are the four layers. I try to give the some examples of this putting these things. If the paper of the paper or skins we are putting the alpha rays and beta rays, gamma and neutrons, how these four layers would lead and water or concretes, how they are going to resist the radiations effect to the particular absorbing this particular radiations effect. Now we will look into see the materials journey. How is the 19th centuries to this current scenario is 2026. There are the segments I have kept in the segments how things is going on. So sometimes you may see the 20 years, or sometimes you may go up to the 30 years or 10 years. So these are the alloys which is being used in the initial stage of this the space aircraft or space industry, as well as the spacecraft or defense. Nowadays, these are you can see here's the wooden and timbers they are used that times only, but right now they are using the difference here. In 1970s scenario, they are using started to using the ceramics and metals composite. Before that, in 60s they used to the nickel based alloy. Yes, obviously still it is there, but they are going to reduce their utilizations maximum percentage. They are using the different kind of the alloy. So rightly in the 2010 and beyond they are using the safe memory alloy, and they are likely to be adopt the high entropy alloys for their betterment and the new sustainable materials applications. So we can see here the properties wise their adaptability functional, every functional adaptability is very easy for this particular the high entropy alloy, and they are having the challenges because the high entropy alloy development their challenges is the manufacturing complexities and the high cost. So these two parameters are the challenges parameters, but apart from that the applications part if you will see there are the very large scope to the deployment of the high entropy alloy for the applications in terms of the defense, in terms of the aerospace, in terms of the automobiles industry, in terms of the marine engineering. So these are the timelines which is used. But now we'll be have a the look into the high entropy alloy for the futuristic materials. Generally, we are at the concept in that pure alloy will be having the singles best pure alloys. Either it is the aluminums or magnesiums or nickels, coppers, irons, chromiums. These are the single best alloy. But in terms of the high entropy alloy, we can see that there are the conventional alloy. And once the conventional alloy and pure alloys is going to mix together, so they can form the different alloys. That will be the new introduced alloys, the high entropy alloy. Basically, initially the Cantor alloy is the very famous for the high entropy alloys because the Cantor alloys are having the very everything, the combinations of the five elements, and it's having the very good properties. So once we are talking about the high entropy alloy, always we take the reference of the Cantor alloys. So you can see the basic five principle or more than the five elements should be there. So they are going to consider as the high entropy alloy. Not only that, we need to be there the five elements. It sometimes there are the chromiums, iron, and nickels is there. So these three alloys can be the approximately the 75% authors they are uh, recommended, and they are putting their words as the high entropy alloy. So exceptionally, the three alloys can be also considered as a high entropy alloy, and there are different point of the density. Why the high entropy alloy is so popular? In that terms, we have to need understands about this particular comparative chart where we can see actually the figures, the plot is the graphs. It is taken around 300 research articles or the review articles, the combinations of review, research, short communications, few of the patents, and we concluded these things. The high entropy alloys, they are having the variety of the properties, because the single property is not making is the very popular. It comes with the different identity, different the properties, and different properties makes it the uniqueness. So these combinations of the varieties of the properties is going to make is the different level of this alloy. So basically, once we will be talking about the things, the inconel or some titanium or magnesiums alloys, they are the capability, the yield strength. You can see here only the 850 approximately to will be start the inconel alloy to the high entropy alloy approximately the 1200. And there the relatively the wear resistance is the one, the baseline is the one, but here is the it's 2.5, so higher than the conventional alloys, and very less degradations is the compared to the conventional alloy. So the such only the few properties I focused because these properties are enhancing the aerospace material components properties. That's why these three properties I have taken care and kept in these particular presentations, because these properties is generally reflected their life cycle of this particular component. If we'll be see how these things is going to change, if we'll be have the some strength ranging the 1000 to 1500 megapascal and region A, because you can see this particular graph, region A and region B. So these two graphs I am going to represent. The region A graph is the megapascal, the strength, there exhibits the hardness value between, and there the yield strength. And region B, you can see there the substituting the density wise, how the density is going to reflect and what will be the effect on this particular the hardness and the yield strength. So there are the two different density wise, density and hardness. It will be directly proportional to the yield strength. Now, the things is to be the how we are going to select the materials. This is the very important slides, because here I have put the seven segments. So the seven segments is the seven segments. 7S is I have kept it there, and in that you can see the highlighted part is the lightweight elements. So these are the periodic table. Particularly, this is the periodic table completely made by based on the high entropy alloy. And high entropy alloy, once you are going to choose the high entropy alloy, what kind of the parameters you need to be take care. First, the what is the their melting temperatures, and what are the density, and what will be comes under the which segments, like lightweights or layer refractory. So lightweights there are the six. So the lithium, beryllium, magnesium, calcium, ascardium, and strontium. These are the six things which comes with the lightweight elements. If we will see the next one, the refractory ones. So refractory having these are the nine particular metals or elements. We can say that the basically elements. These nine elements is going to produce the refractory elements, means high entropy refractory elements. And if we will go for the commonly used, so these are the commonly elements we are going to use for the developing the high entropy alloy. And less use if we will see in that, so these are the metals or elements which is being very rarely used for developing the high entropy alloy. Simultaneously, if we will talk about the transition series, these are the transition series, and transition series are using for this the high uh, temperature. It has be around the 23 degrees Celsius, or maybe beyond the 23 degree or 2400 degrees Celsius is required for this developing the that high entropy alloy in the transition series. And the lanthanide it is the different part, different elements, because very rarely, rare of rarely, they are going to choose such kind of the elements to forming the high entropy alloy, because it's required very uh, ranges of the temperatures, and that temperatures you can maintain it, but the things once it's developed, that their properties wise and their applications wise is not too much fruitful. And here the last one is the rarely used elements. So these are the rarely used elements for development of these high entropy alloys. Look into this particular. The next is the what are the key challenges, as I discussed. The challenges in the selections of materials, the high strength weight ratio should be there, because sometimes the due to the higher side of the density can disqualify for the material selections. And it should be the extreme thermal and mechanical stress is be there, durability against the radiation, atomic oxidation is be required. And last one is the very important part, that their expenses, because once you are planning to develop from your the furnace maintenance to the raw material procurements, and the final coming with the product waste are developed the small quantity or maybe the lab skills of the alloys. So these kind of the things we have to be maintained, because the analysis is very scalability is required, because due to the higher side of this metal cost, if you are going to buy them or purchase them, so what will be the effect, or what kind of the targeted components you are planning to develop through this alloys, developed alloys. So that things you have to be very clearly understand. Now here I have showing you this one small video, and this video is just you see this the video. Recently we have installed these things, and we have developed to a high entropy alloy through this vacuum induction smelting furnace. So actually, basically, we have installed the very recently up to the 2200 degree Celsius temperature vacuum induction melting furnace, and it has the capability to melt this very good of the particular high entropy elements, whatever the ranges is required for our the pilot projects and all. Now, if we'll see the few of the results. I have just concluded the few of the results. How the microstructures is coming with this particulars, the alloy once you are developing, and what are the effect we can see in the TM analysis and the tensile testing. So currently it is the very less because it is the basically the we have kept the rather the maximum portions of the 35% of the part of the aluminums because in the singles, and the another part is there are the some different tin is there and zinc is there. So few of the things we have kept is there. So in basically we have to be improve the different, because the once we have developed the high entropy sites, there are around above 1200 degrees Celsius materials which is going to melt in that particular furnace. There will be the some different strength and all. This is the just for the screening and for the just one examples we have kept there, because it is the lightweight high entropy alloy based on the aluminum parts we have taken care. Now will we see what are the market size of the high entropy alloy and what kind of the work we need to be taken care. So it is the complete the market size if we see. So there are the very good market size in the high entropy alloy, and the very latest research also is taken care by the very good universities and India is also having the very good academic and laboratory based in our field, the scientists are working for that particular development these things, but we are facing some challenges and all, so we need to be sort out this thing. There are the challenges and some tentative the solutions we are looking for the problem. The productions of the manufacturing complexity is there. So development the cost effective the bulk productions techniques, that things is required for this. The complexity the governing the effect of the high input alloy, because there are the four effects is there, and the four effects we need to be taken care for that. And the computational modeling techniques, that is the Kalfad methods is there. Kalfad methods we can use this Kalfad with the software analysis. In that we can simulate the particulars high entropy alloy mixers, and we can get approximately tentative their ratios wise and their effect. Then we can go for this real product applications or productions of this high entropy alloy. Requirement of the precise method to identify the composition for industrial use. So AI driven tools nowadays is coming out coming in this market. So in that using we can see that these things and unexplored applications despite the extensive research. So the lot of the white space is there, so we have to find out the gray part of this particular applications, and our conclusions should be there. If you are going to contribute few of the component based on this high entropy alloy, so that will be the biggest contributions for this particular industry and automobile sections and all. So I have this the research teams, and another research teams are there, but they are not working in the metal, they are working in the ceramics, and they are basically work for this the synthesizing of the SiC. So these are the basic profile, and I hope this times is very good for us. And if you have some questions and some things, you may put the questions and all. It will be possible to then reply. So, Professor Dr. Patra, please, if you are there, then you may ask to our participants, or maybe Dr. Behra is there. So, please.
Yeah, Dr. Rajak, thank you for such wonderful insights regarding high entropy alloys. I think this is the first talk of today's session, and you have nicely illustrated the different aspects, and specifically how the manufacturing is done. Now, if anybody has any question, so they can start ask. So we will have some time so that we can get more inputs from Rajak. So one by one you can ask if anybody has any question.
Can we get recording of this session?
Good morning, sir.
It can be little louder. Those who are asking question can be little louder so that it is audible
Okay, sir.
to the speaker. Yeah, go on. Yeah.
Sir, good morning, sir.
Good morning.
Am I audible, sir?
Yes,
Yes.
you are audible.
Yes, sir. Sir, my name is Jagdish Shah from NIT Calicut. Sir, what is the research that is going on in terms of the magnesium alloy? Because the magnesium alloy is lighter than the aluminum alloy. And what are the possibility of research in the magnesium alloy with the high entropy or medium entropy combination, sir? And is there any application in CSIR for magnesium alloy, sir?
Yes,
Or
actually, Professor Jagdisha, actually, we are working on that, and you may see last my research associate, they are working in magnesium alloy only, and we are also using in high entropy alloy development for high entropy alloy. But due to the some oxidations and flammable properties, we are not
yes.
going to consider for the induction melting furnace, but we have the arc melting furnace. Over there we are putting the some inert environments like argon gas environments, and we have developed the magnesium, aluminum, zinc and tin. There are the four combinations of the high entropy alloy. So basically, it will be called as the medium entropy alloy. It won't
Yes.
be called the high entropy alloy. It will be called the medium entropy alloy, because their density is the less than it is the less than 1.09
1
R.
point, yeah, sir, 1 point.
09 R.
Yes.
So this things is there. So we are working, and also we are also using this particular magnesium alloy in different orthopedic applications also, because current project is going on based on the magnesium alloy, and we are replacing the aluminum alloy, that is the LRA unit, the line control unit, which is being to use in the aircraft. So we are putting that coating on that, copper coating, or copper graphene composite coating we are putting on that, and we are replacing to that aluminum, that 2024 is their series is there, aluminum series is there. So we are going to replace on that particular magnesium sheet. So there are huge applications, and as you told, it is the lighter than of the aluminum obviously, but due to the some of the properties, we are considering it for the different applications, and we are going to composite it. So
Yes,
it
sir.
has the very huge applications.
Sir, thank you, sir. And the magnesium alloy, basically, the problem for a biomedical application is the corrosion, sir.
Corrosion, correct.
FDA is actually we need 0.5 mm per year, but the corrosion rate is quite high,
Above
around
one.
3,
Yes,
around 3,
above
4,
one is
like
there.
that. If it is not extruded, it will be around 2 to 3, and
Correct.
like,
So
yeah, how do we actually tackle that problem, sir?
Professor, you can see rightly. I am also did some the corrosion tests, and we have got the 1.6. So
Okay,
that
sir.
because we have put it the 200 microns the electroplating coating,
Sir.
so that copper deposition is there.
On the magnesium alloy, sir?
Magnesium
Okay, sir.
alloy. So we have done the roll milling, and based on the roll milling, we have created one sheet, that is the 2 mm thickness sheet, and in that we have done the electroplating, copper
Okay, sir.
electroplating, and
Sir.
that copper electroplating process we deposited in the particular that depositions, and we got the corrosion rates 1.6, and it's also enhancing the thermal and electrical conductivity, because magnesium having the low thermal and electrical conductivity as compared to aluminum.
Yes, sir.
So
Yes, sir.
these three things, it's so poor, like corrosion, thermal and electrical in mechanical point of view, and biomedical it is for corrosion effect.
Corrosion. Yes, sir.
So we can enhance that putting the nickel coating, or maybe that rightly I am doing that copper coating electroplating process. So it is going to reduce the thermal corrosion effect.
Okay.
So
it should be like, is it for the structural or for biomedical, sir?
So it is for structural. I am just looking for the structural application.
Structural. Okay, structural.
Because another two, electrical and thermal conductivity, I am also considering.
Yes, sir. And 1.6 corrosion rate, you got it without any cryogenic treatment, sir?
No, cryogenic NaCl 35% cryogenic treatment is there. So after corrosion treatments that we have done,
it will reduce. It will reduce.
It will be reduced. It will be reduced. But after coating only. After coating.
After coating, you tried cryogenic, sir? Cryogenics.
Yes, yes, because before it will be around 2.8 or 2.6. Where AZ91E, talking a specific alloy, magnesium AZ91E. So it is very specific alloy based on the magnesium.
Okay. But where is this AZ91E alloy is used? Because 318 and such kind of alloys are used, no, sir? Where
Yes,
is
yes,
AZ?
318W was
Ah.
because actually I am looking for that AZ because AZ91 means 9% is the aluminum and and the baki remaining thing is the magnesium is there and 1% is the zinc is there. Correct. So
Yes,
in
sir.
that I am looking for the LRU unit application in
Yes.
aerospace. LRU is there.
Okay, sir. And can we use this, star casting method for this magnesium high entropy alloy, sir? Star casting method like ordinary star casting method or
Actually, we can use, but as our
because melting
first,
temperature is quite low, sir. For
because
750,
around the
800 enough.
because it is below the 600 and below the 600 whatever the things you are going to develop, I think
Yes,
it
sir.
much not seems it's good to go for the structural application and other applications once you are going to add on magnesium.
Yes, sir.
So we need to think on that beyond the actually high entropy alloy. Once you are talking, so we need to go means extreme environments. Either it is cryogenic or either it is the high temperature.
Yes,
Then
sir.
only it will be worthy. Otherwise, the single alloy is sufficient.
Yes, sir. And during this melting, sir, this if you have magnesium and a very high, zirconium oxide or zirconium is added, their melting temperature is very difference is very large, sir, and
Correct.
this may cause a agglomeration problem or a non-distribution of the zirconium or zirconium dioxide, especially for strength application or agglomeration problem. How do we avoid
Yes,
this
yes.
kind of?
See, actually, that is the zirconium is the refractory elements. Okay.
Yes, sir.
So zirconium, if we are talking into magnesium, so in that refractory alloy or elements, metal alloy, you are going to mix together. So it will very rarely blend. So
Yes,
we
sir.
are not going to try like that refractory to the elemental. So we are
Sir.
putting our that periodic table. So sequence wise, elemental group is different and the refractory group is different. Yes, yes, we can't mix together rightly because the initial stage you have to take care about the group wise,
So
which
group
group
wise.
are having the near about the melting point like nickel, copper, nickel, chromium and iron. So near about 200 or maybe 250 degrees Celsius are differences from each other. So
Fine.
in that you can manage it because sometimes if you're putting around 600 and we are talking about 1800, so it is a large temperature gap.
Large different temperature, yes.
Yes, yes. So it will be very difficult to merge it and stirring it because high temperature stirring is very difficult. And
Very,
once
yes,
your metal is charging, its process is there, so metal charging is very difficult. And homogeneity is not there, then your alloy won't be perform as good.
yes,
So
sir.
we have to be
Yes,
take
sir.
care
Yes.
a lot.
Yes. And even even with the master alloys also, this problem is also there, sir. Like
Yes, yes.
yttrium,
Yes, yes.
yeah, yes, sir.
Correct, correct. It is there. It is there. Master alloy is also there.
Okay,
Thank
so
you
I
very
think
much. Thank you very much, sir. Thank you
yeah.
for your time,
Yes.
sir. Thank you.
Yes,
Sir.
Professor Patra, please.
Yeah, anybody else from students? Any question? The students, it's a session has been organized so that all can learn from our expert speaker. From student, any question? Okay.
Good afternoon, sir. Good morning, sir.
Morning.
Sir, can we just suggest that HEA or the high entropy alloys are having future in hydrogen storage as well, as far as magnesium based are concerned?
Yes, yes, yes. Many of the researchers in India, they are working for storage the hydrogen energy based on the high entropy alloy. Most of the things are some IIP, Dehradun's, some and that BHU and few of these IITs, they are working for storage there because see, high entropy alloy not is the limited and it having the max phase also, maxine. So max phase up you can develop and we are also looking for because AMPRI is also going to another the scientists they are working for storing the hydrogen energy. So it is work is going on. You may also look into that particular literature and all, and you can also start their work. There are scope.
Thank you, sir.
Okay, we can take on only one question. Anybody else want to discuss? Any other participants? Okay, if there is no question, so once again, we're going to thank Dr. Rajak, and who has very nicely shown how actually the real production is going on. Okay, so just before I sign out, one very interesting question come to our mind. Dr. Rajak, is there in India, because I also going to present one of the talk on techno commercial aspect of high entropy alloys. Means from your perspective, how much is Indian market at present are going to means having beneficiate from the laboratory scale, because it is now I think confined within laboratory scale. Is any industry comprehensively developing high entropy alloys for commercial application? If you can throw some light on it.
Actually, Professor Batra, few of the literatures I have seen, and I have go through the lot of industry website, and few of this particular, specifically, I am looking for this space or aircraft manufacturing industry. Those who are working on that are developing the component, which is they are using the some raw materials or different alloy for developing this the particular components. So I went through the lot of industry, the contact and all, but the Indians that companies, they are not particularly ready to accept this new materials for their development for this component and all. So the Indian market is there. Indian market I went through, and but compared to the that is only the lab scale. So very rarely of these particular manufacturers like the energy storing and that biomedicals also they can use that aerospace, marines, and different sustainable wings they are using for this particular high entropy alloy. So it is going to use. I have the I can share you the data where there is a particular the things, because I have created around approximately 1200 literatures, the sites and all that review papers and articles. So I created one the index, because very soon one of our that authored book is coming in the high entropy alloy.
Oh,
So in that I have kept in index also. So annexes I kept the what are the market size in India and across the world. So these are distinguished, and what are the research trend in going on in the India and outside, and how the Indians academicians, how what are the contributions, what are the research laboratory contributions. Like that, I have created one the graph and all these things very clearly, picturely. It can be visualized. So that things I can share with you.
okay. Yeah. Okay, so I think we have a very nice.
Sir, I have one question, sir.
Yes. Who is there?
I am Abhinandan from IIT Kharagpur.
Please go ahead.
Sir, I am asking that if I am going to mix some metal powders, basically for preparing a high entropy alloy, let's say if aluminum is there and zirconium is there, so there is a large density difference of them. So is there any possibility of segregation while melting and developing that high entropy alloy? If they are, how to overcome that?
Sir, actually, as one of the professor from NIT Calicut, he was asking about the Professor Jagdisha, he was asking the same questions related to that, because there are the very temperature gaps. So we are not supposed to be, because as per my experience, I haven't tried it things that aluminum and zirconium, because zirconium itself having this the refractory elements. So I never tried right now, because also exploring the things. Once I will be explore, then I can understand the basic principle fundamentals, the concept, how it is going to mix together. Because a lot of things it may be going to stop to the developing the high entropy alloy, because there won't be proper mixing, homogeneity will be there, and their density ranges will be makes the difference. Another properties can be maybe hampers and all those things. So rightly, I am not on that developed particular that zirconium based and aluminum and zirconium combinedly. So it's critical to say you something because it's a very unique things. I can't say completely.
Okay, thank you.
Okay, sir.
Okay, so I think we have come to the end of today's talk, and once again I thank Dr. Rajak, who nicely explained all the doubts and clearing, providing very useful inputs, okay, regarding the high entropy alloys. So thank you, Dr. Rajak, for your time and agreeing to the to be an expert speaker for the 5 days short-term course. Thank you once again for your time. Thank you.
Thank you, Professor.
Okay, so the next session we will start from 2:45. Dr. Shailesh Kumar Singh, he is from CSL Lab, Indian Institute of Petroleum, Dehradun. He will be talking on application-oriented high entropy alloys. So please sign in by 2:45. Okay, so you can sign in 5 minutes earlier so that you can have easy access to the presentation. So thank you.